Hello, my name is Andrew Geary, and welcome to Seismic Sound Off, in-depth conversations in applied geophysics. I'm joined by Igor Kvasov, engineering manager at Google and co-author of the recent book, Numerical Modeling of Seismic Responses from Fractured Reservoirs by the Grid Characteristic Method. Igor and I discussed just what is the grid characteristic method, the advantages of this method, why numerical modeling should be used more in survey planning, and Igor's challenge to the geoscience community on numerical modeling. For more on this cutting-edge book and Igor Kvasov, visit seg.org/podcast. This episode is sponsored by TGS. TGS is a global gateway to subsurface intelligence from seismic to well data. As a leading geoscience data provider to the energy industry, TGS invests in onshore and offshore multi-client data projects in an array of basins worldwide, ranging from new entry frontier markets to established mature basins. TGS's extensive data library portfolio services the entire upstream life cycle, from exploration through the appraisal and development stage. Leveraging the breadth of this world-class library, TGS enhances the exploration process through advanced analytics and analytics-ready data products. Now, for our conversation. The book that we're talking about today, it's divided into two parts. Just for the audience to get familiar with the book, what is the general outline of each of these parts and how do they complement one another within the book?
So this book is actually a mix of heuristic method of numerical modeling. That's how we approach this numerical modeling. The entire book is based on this advanced numerical modeling. And this is the first part of this book. It's a very good description of this numerical modeling approach we use. And the second part of the book, this is part one, and part two of this book is application of this method to various practical problems. How to identify fractured zones in media, how to map them directly. In 2D and 3D, we are talking about macro fractures, mesofractures, individual fractures, clustered zones, and so forth. So part one is the method itself, a lot of math in there, and part two is application of this method and results of numerical computations for practical applications.
And for people who might be scared over the math, the applications of the method it's a larger part than the math section. So I'm sure you can get a lot out of it, even if you don't want to dive completely into the math.
Correct, yeah. So while working on this book, we were arguing, authors, whether to include math or not, move it to appendix or not. But finally, we discovered there are two big audiences for the book: mathematicians or math researchers who are willing to know about this advanced numerical modeling approach, grid characteristic method. And the other audience is about geoscientists who just want to look at the results. We got new results using this method. Of course, there is an overlap between these two. However, the book is perfectly fine for both of them. And say if you want to skip the math, so you can just read the summary of the first chapter, the first part. And yes, second part is way bigger.
So as you mentioned in the first question, the grid characteristic method is a major centerpiece of the book. Could you just briefly explain this method and highlight how it does have advantages over other methods?
Sure, yeah. Grid characteristic method is the closest to finite difference methods. However, it has some advantages. So in particular, it takes into account that we are dealing with hyperbolic equations. So this type of equations that are not typical, but that govern wave propagation. So it takes this into account directly, and it enables a few key properties and advantages of grid characteristic method. First, there are no numerical oscillations or other artifacts of numerical modeling by design. Second, we are able to set mathematically and physically correct boundary and contact conditions between layers in media and on boundaries of fractures. And third, we don't really need to use any averaged media instead of fractures. This method allows to model directly up to 1 million of fractures. Usual approach, which other methods have to use, is averaging. So say if you have a lot of fractures or cavities or some inhomogeneous media, so you need to come up with some averaged media instead. With our approach, we can model them directly, and we can analyze scattered waves from all fractures directly. No need for any approximations. Thus, it enables high accuracy of this method.
Just going into a little bit more detail, how does the grid characteristic method address the challenge of analyzing fractured media?
I don't want to go into math, so we just do some massaging of governing equations of elastic media, which enables us to split the underlying system of differential equations into simple transport equations. And these transport equations can be solved with high accuracy. Then we transform the solution back to the original form. And thus it enables us to set correct boundary conditions on every single fracture. Not sure if it answers your question, but this is as far as I can go without going into math details. I encourage listeners to just read through the first part of the book.
Absolutely. Go check out the book for more details on that answer there. What is promising about the area of numerical modeling to you?
I think the main advantage we are trying to convey with this book and then a new discover is that, well, we can actually model everything, every single detail about the model, even if it's not really known. No one really knows how fractures are positioned, are oriented inside Earth. However, you can make some assumptions, and you can see how your wave response, varies depending on fractured parameters, how they're allocated, whether they're fluid filled or gas saturated, how they're oriented, and so forth, and so on. So you can actually analyze all these aspects, and we've proven this book that you can actually map your fractured zones directly using direct response, using scattered waves without any further analysis. So this is really powerful, and for so many years, numerical modeling used averaged media, which kind of eliminates all these fractures altogether. So all signal is just lost. If you are able to model all these structures directly, this is really cool. And with increasing computing power, yes, you can finally do that.
So what motivated you and your co-authors to write this book?
We believe that current methods of data acquisition and seismic surveys can be much more advanced if they could use multi-component registration and actually get use of all these components. We've proven in the book that it is possible to direct mapping of fractured zones is possible based on scattered waves directly. It actually enables discovering of fractures and oil and gas reservoirs much easier, although these methods are not yet in use. And this is the future of data acquisition and seismic surveys. So we want to bring advantages and new approaches to seismic survey.
It was kind of answered in some of in that question and your other responses a little bit, but more directly, just in case there's something else to add, what makes this monograph unique in your mind?
Yeah, I think I covered it in the previous questions and just want to reiterate on that because this is really a keystone of the book. With grid characteristic method and with parallel implementation of numerical modeling, we are able to model all fractures up to millions of fractures directly, both in 2D and 3D, and it enables new areas of numerical modeling for fractured zones. Using this method, we were able to map fractured zones directly, and it will be of great use for seismic surveys.
What insight or two did you gain in writing this book?
I believe that numerical modeling could be used much more extensively in data acquisition and data planning, seismic survey planning. So before even going to the field, you can use numerical modeling to get an idea of how to position your receivers and what kind of signal you should expect and what kind of analysis you should apply on your data. Designing your seismic service is a key, and you can save millions of dollars by just doing it better. And numerical modeling could be used much better. I think it's not of that much use. So I know that a lot of people use simple ray tracing for survey planning. However, more advanced, like grid characteristic method could be used, and you can get much better idea of what to expect and how to analyze your data. We've proven in the book that by simply analyzing your scattered waves, you can differentiate by the you can tell apart different fracture types, different fracture zones. You can actually map fractured zones directly by looking at the response. So this is really powerful, and I believe that there is a lot of future in numerical modeling for seismic survey planning.
What will surprise the reader the most in reading this book?
While discussing this book with other researchers, I discovered that there's a lot of attachment to averaged media approach. So I think this is a really surprising thing that averaged media is just a replacement for inability to model fractures directly. And we enabled this direct modeling of all fractures. So there is no much need for averaged media any longer, as long as you can model all fractures directly. It could be still needed once you really understand why you're averaging media this way. But as a first step, just model all fractures directly, and then you get a better idea of what kind of averaged media you should use.
What do you see in the next 1 to 2 years for numerical modeling?
We're actually working on the next book already, and we just apply this grid characteristic method to other problems, including micro seismics, including time lapse. So a lot of problems in these two areas, and this numerical method works really well for them. So we work with a lot of people who are interested in numerical modeling, and we actually provide them. We partner with them, and we provide really insightful results into all this problem: microseismics, time lapse, and averaged media approaches. Like porous media is another example which we can model directly. So there are a lot of arguments now what averaged media to use for porous media, and we can solve this directly using numerical modeling. Stay tuned.
How exciting. There'll be a sequel forthcoming of this book. What thought or challenge would you like to leave the geophysics community on this topic of numerical modeling?
I think the main challenge is not the method itself, is not the problems itself, but how to incorporate numerical modeling into oil and gas exploration better. So I still feel that numerical modeling is kind of on the side of current processes of data planning and seismic survey planning and data acquisition. So the key question that bothers me is how to utilize the power of numerical modeling better.
Well, that is great. I appreciate you, Igor, taking time to explain a little bit more about these methods and what their use is and the positive things ahead.
Absolutely. You're welcome.
Now is the time to renew your SEG membership. SEG members create meaningful professional relationships through expansive global networks, enjoy free access to the leading edge and the SEG library, and can save on SEG bookstore purchases and annual meeting registration. Learn more and renew your membership at seg.org/renew. And thank you for listening to SEG's flagship podcast. Please share this episode with a friend, colleague, or manager that would enjoy hearing this episode. Your recommendation is the single best action you can take on behalf of SEG's podcast. Go to our website at seg.org/podcast to find all our episodes and learn the easiest way to listen directly on your phone. Original music by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Geary. The SEG podcast team is Jennifer Crockett, Allie McGinnis, and Mick Sweeney. Thank you for listening. This is Seismic Sound Off, signaling off.